Thank you very much for the very kind introduction and for the invitation to give this Boeing lecture. I think it's my second one. The other one was 10 years ago. So this time I'm going to talk about invisibility, which is a subject of interest to humans for millennia, starting at least from the Greeks, Perseus versus Medusa, and in many science fiction books and movies and comics and so on and so forth. So let me show you a clip, trailer, of some four of the most recent science fiction. I hope this works. Okay, so that's a trailer. So I selected this because they have something scientific about invisibility that I'm going to use later. So in the Invisible Man, the movie that you saw, was based on the famous novel by H.G. Wells. And he was a chemist, and he made himself invisible by changing the index of refraction to be the same as of air. So the index of refraction determines how you see it, what you see and how much you see, because particularly one sees from the reflection of light in our eyes, and also there can be scattering, diffraction, many type of situations, but if it is the same as of air, the rays of light will go straight through. So that's why his face is invisible. You can see the clothes because the clothes have not changed the index of refraction, and the rays of light will reflect and will get your eyes. So of course this is not recommended. This is a dangerous procedure. He tried to reverse it, and also unlikely to work because the human body is very heterogeneous. The index of refraction of different tissues is very different. So don't try it at home. But however, the idea of changing the index of refraction is a good one. So my son, who is a comic fanatic, pointed out to me when I explained to him the ideas behind invisibility that this is what the Invisible Woman does. It's Susan Storm Richards. It's a comic from the Fantastic Four, I believe. So she makes herself invisible by some field of energy that we don't know how she creates, that makes light go around her. So light doesn't reflect or scatter or does anything because of this field of energy that deflects light. And so again, we don't know how to do this, how she does this, but the idea of making light go around is a key one for the ideas I'm going to explain later. And Star Trek in the cloak Romulan Birds of Prey, they do the same. This ship turns itself invisible by putting gravitons. This is the first connection with the general theory of relativity. By the general theory of relativity, Einstein says that there's a large mass, then space-time warps, bends. So light will bend around. And this is, so they create these large gravitational fields with these gravitons. Of course, how do you do that? That's another question. And then light will be deflected, and you won't see the ship when this is turned on, because the light doesn't get to your eyes. And of course, when you want to be seen, you just turn off the gravitons. Because again, the idea of deflecting light is a good one. But how to do this for optics, for electromagnetic waves, as I'm going to explain, that's what I'm going to try to do in this talk. And the way we're going to do it is like Harry Potter, by creating a clock. So we're creating a clock. When you put it on, it has such an index of refraction that deflects light. So you're changing the index of refraction of yourself, but not by the chemical procedure, by putting a coat, a clock, and that makes light go around. So that's the way Harry Potter becomes invisible. But again, how to create this clock, and this is what I'm going to try to explain. And this is myself half invisible. Here also, my hand invisible. And so the scientific idea that, as the title of this talk, is called transformation optics. It's a mathematical idea, a very simple one. Use transformations, how to transform an object to another one. And this appears for the first time in my paper with Alan Greenleaf and Matti Lassas, studying an inverse problem, which I will explain in a little bit of detail. Calderon's problem, also called electrical impedance tomography, which was published in 2003. And a short rocket conductivity that cannot be detected by EIT. EIT is electrical impedance tomography. So this is the more applied name for Calderon's problem. And the same transformation that we use in these papers was used by Penry and co-authors in a paper called Controlling Electromagnetic Fields. And another transformation was considered in 2 dimensions by Ulf Leonhardt in the same issue of Science in 2006. So the idea is using transformations, but how to use transformations. So this is explained rather well in this article in Science magazine, The Ultimate Camouflage. So the real breakthrough may lie in the theoretical tools used to make the clock. In such transformation optics, researchers imagine a la Einstein warping empty space to bend the path of electromagnetic waves. This is the idea I already mentioned, that's present in the Invisible Woman and in the Star Trek ship. So you try to warp space so that the path of light, which is an electromagnetic wave, goes around. A mathematical transformation then tells how to mimic the bending by filling and warp space with a material whose optical properties vary from point to point. That's translated into changing the index of refraction that will vary continuously, and the technique could be used to design antennas, shields, and myriad other devices. Any way you look at it, the ideas behind invisibility are likely to cast a long shadow. Well, we don't want a shadow. we don't want a shadow, because if you have a shadow, you can say something about the object. So there is no shadow in this invisibility cloak. So this is a cartoon from the paper of Penry et al. What we want to do this is a section of the clock. The blue is the clock. In the orange ball here, or radius R1, is Harry Potter, or whatever you want to put. And here, one uses a ball, but can use another shape. It doesn't have to be a ball. And then the clock is from R1 to R2, and then the rays of light go around. And when you observe outside the clock, it looks like light went straight through, like in the case of the Invisible Man. So we need to create this blue area here, which is the cloak of invisibility, so that light goes around. Okay. So what we did in the paper I mentioned in 2003 is we did this for conductivity. Conductivity tells how much current goes from one place to another. Is the inverse of the resistivity. And these are actually the waves for the case of for the steady state case in electrostatics. So the left is the conductivity 1. So the arrows are the currents, and they go straight through. So we created a conductivity such that the currents go around the object. But when you observe them outside in this boundary here, outside, then it looks like it is the same as the ones in the left. So you cannot distinguish between the right and the left. So whatever you put inside here is invisible to electrical currents. So you cannot find it using voltages and current fluxes. And the same thing happens for other models. For Maxwell equations, that's light. You will have the same situation. The waves will go around and don't penetrate here, but when you observe them outside, it's the same as the case of homogeneous medium, like air or vacuum. So as I mentioned before, in Einstein's theory of relativity, bending light is done when you have a large mass like the sun here. So light is deflected because this is a large object. Again, space-time is warped around the sun. So when you see a star, a distant star, in a certain position, you're actually seeing it in the wrong position, is because of this deflection of light. This is called gravitational lensing, and is used in cosmology to see where the stars are, because we have a lot of information of large masses in the universe. And the opposite process occurs for a black hole. For a black hole is the other extreme. After a certain position, it's called the event's horizon, light will not come back. That's why it's called black, and cannot escape, and everything becomes dark here. So we want to do the opposite. I call it an optical white hole. This is for electromagnetic waves, meaning for light and other type of waves. There is a large spectrum of this type of electromagnetic waves. So we want the light or other waves to go around and not penetrate here, so this object becomes invisible. That's what we want to create. And first, the ray theory of light. This is very useful theory. It's based on Fermat's principle. Fermat's principle says that light, from going one point to the other, takes the minimum amount of time possible. But the minimum time depends on the speed of light on the medium, because times is the distance divided by the velocity. So it depends on the index of refraction or the velocity of light. The index of refraction is essentially the inverse of the speed of light. So in this case, this is the index of refraction is high, the blacker regions, and then decreases. So light is not going to go along a straight line. It's going to go around. It's going to bend. And many phenomena can be explained with the ray theory of light. For instance, when you see a straw in a glass of water breaking, then this corresponds to the fact that the air and water have very different index of refraction. So in order to go from one point to the other in the minimum amount of time possible, light will break. And you see the fish, similar to what happens for a large star, you see it in the wrong position because of this breaking of the light. This is what you see in a straw here. And this index of refraction that I showed earlier occurs in nature. It happens, for instance, in the desert. I don't think it happens very often in Seattle that you can see water in the road. But in a mirage, in the desert, this is very hot here. The index of refraction is very small, and it increases as it goes up. So when you're thinking you're seeing water, you're actually seeing the sky. So the ray theory of light can explain this mirage phenomenon. But it doesn't explain everything. There's, for instance, diffraction, interference, and so on. And there is a question of whether full wave clocking, not only for the rays, is possible even in theory. And this is possible, and I will show you how to do it. So this is based on the wave theory of light, which was one of the great triumphs of civilization. Of course, Maxwell was based on many other people. He completed the equations, it was called Maxwell equations nowadays. And one of the great discoveries of all time, that light is an electromagnetic wave, and the velocity of this wave is the speed of light. And this has been confirmed many times, and the number of applications of Maxwell equations is just goes forever and ever. Television, radio, computers, etc. Anything that uses electromagnetic waves is based on the wave theory of light. If there would be patents at the time of Maxwell, if he would have patented, he will be trillionaire many times over. So this is an electromagnetic wave, has an electric part and a magnetic part. And the parameters of any medium has electromagnetic parameters, the electric permittivity, the magnetic permeability, and the relation with the index of refraction is the square root of epsilon times mu. And the ray theory of light is really a high frequency approximation of the Maxwell equations. And these are Maxwell equations. These are for time harmonic waves. So you take a wave of the form e to the I omega t times something. Usually it's the derivative with respect to time, but I'm taking time harmonic waves. And E and H is the electromagnetic field, D is the electric displacement, and B is the magnetic displacement. And one important feature of the medium that we're trying to build, we're trying to find epsilon and mu for the Harry Potter's clock. What should it be so that we have this phenomenon of light going around? And this will be anisotropic medium. Anisotropic means that the electric displacement is not in the same direction as the electric field. This is a matrix. And the same for the magnetic field. And most materials actually are non-magnetic with mu equal to 1, but here we're looking for different type of materials, and mu will be anisotropic also, so will be also a matrix. And of course we have, in this case there is no density, and we have no magnetic monopoles. And so I'm telling you the answer, but I will explain how to obtain this answer. For the mediums that we need to have this light source ray or the waves go around an object, is the epsilon has to be equal to the mu and equal to some matrix, semi-positive definite matrix, inverse times the square root of the determinant of G. So this will come again and again. So this will be a matrix that in mathematical terms this is also called a Riemannian matrix, but that doesn't matter, it's just a matrix. So let me start with a simpler situation that has many of the features of Maxwell's equation, which is Helmholtz equation, which models acoustic waves or quantum waves. This is the Laplacian for this metric, G. So it's written in this way. It's called the Laplace-Beltrami operator in differential geometry, but you just take this 1 over square root determinant of G. And this here appears this factor again, square root determinant of G times G upper ij. This is exactly this. So this is the coefficient that appears in Helmholtz equation in this case. And in the case that this matrix is identity matrix, this is just the standard Laplacian, the sum of the second order derivatives. So this is Helmholtz. I have uncoupled them here. And first I'm going to consider the case that where this transformation optic was first found, which is the static case, when case 0. This is just, these are called harmonic functions, Laplacian equal to 0. And this is equivalent to what's called electrical impedance tomography or Calderon's problem that I mentioned before. I will describe in a little bit more detail. So we're trying to find some conductivity in this problem by making electrical measurements at the boundary. And the way we got into invisibility is because we could not find certain materials, and so they were invisible. And so this leads to invisibility. But it was by studying the inverse problem that I'm going to mention that it was found. So let me mention briefly the problem. Calderon problem, also in the applied literature, is called electrical impedance tomography. In geophysics, it's called resistivity impedance tomography. The same, conductivity is the inverse of the resistivity. And the question is, can you determine the electrical conductivity, which measures how much current goes from one place to the other, by making voltage and current measurements at the boundary? So you put electrodes around, input voltage, and measure the induced current at the boundary, or the opposite. You can take currents and measure the voltage. And the motivation of Calderon, which is a famous analyst of the 20th century, he developed the theory of singular integrals, for instance, with Sigmund. It was in geophysical prospection. He was an engineer for the oil company of Argentina in the late 40s. At that time, there was no mathematics degree per se. And so most of the people interested in mathematics, they went into engineering. And that's when he thought about this problem, and has been proposed also for early breast cancer detection, because normal breast tissue has much lower conductivity than cancerous breast tumor. In general, blood or water has very high conductivity, and in tumors, cancerous tumors need blood to grow. That's why the reason of the high conductivity difference with the normal breast tissue. And this was proposed as a screening method together with mammography for early detection of breast cancer. This is a cartoon of what Calderon was thinking. So you have a log well here, put electrodes around the input voltage and measure the induced current flux, trying to find whether this is oil. There is oil. Oil has very different conductivity than the surrounding rock. And in fact, the Schlumberger company started by finding oil using electrical measurements. And for mammography, this is a cartoon of what's happening. This have an electrode. This is a compressed breast. You input voltage and you measure the induced current flux, and you try to infer whether it's a tumor or something more specific about the tumor. And again, it's based on that the conductivity is very different. The reason to look at this for screening of breast cancer, that X-rays, when one takes a mammography, there are very few of them. It's not like CT scan where there are many X-rays taken, and sometimes they miss cancers. And so David Axelson has been trying this application. This is Calderon. And he said something interesting in the speech when he accepted the Doctor Honoris Causa from the Universidad Autónoma de Madrid. This was in Spanish. My work at Yacimientos Petrolíferos Fiscales, this is the oil company of Argentina, still exists. It was very interesting, but I was not well treated. Otherwise, I would have stayed there. I was very fortunate for mathematics that Calderon was not well treated here. So what is Calderon's problem? So by Ohm's law, the current at the point X is given by 1 over the resistivity times the change in the potential. And the conductivity can be a scalar, can be a matrix. This is the anisotropic case, the one we are interested in. And then if there are no sources of sinks of currents, the divergence of the current equal to 0. So this is a very simple partial differential equation. It's elliptic. When gamma is equal to 1, this is just the Laplacian. Divergence of the gradient is just the Laplacian. And so you input a voltage potential on the boundary. This is called the Dirichlet problem. And you measure the induced current flux at the boundary. So this is the normal component. The mu is the unit outer normal of the current. And the information is encoded in this map. To a voltage potential, you map it to the induced current flux. And the inverse problem, EIT or Calderon's inverse problem, does knowledge of this map determines the conductivity inside. It's a very difficult inverse problem because the currents go all over the place immediately. It's a very diffuse problem, so it's very hard to capture where this came from because of the diffusivity of it. In the boundaries, you get all kinds of information. In mathematics, this is called the Dirichlet to Neumann map, maps Dirichlet data, and this is called Neumann data. And the problem is the following, and then I'm going to write it in the anisotropic case because that's going to be the case of interest. Can you recover the conductivity knowing this map? And this is the key, one of the keys. There are two keys. The answer is no, you cannot. You take a change of variables, for instance, a rotation inside the domain, which is the identity of the boundary. So this matrix is not going to change if we make this change of variables. So this is the identity. Then this new matrix, which is the Jacobian matrix, the matrix of the derivatives of this map, transpose, composed with the matrix gamma, composed with the Jacobian divided by the determinant, composed with this map inverse, gives rise to the same, exactly the same conductivity. It's called the push forward of gamma. And how do you see this? Is because if you change variables into the equation, this is invariant and the changes of coordinates, meaning when you change u to compose with psi inverse, you're going to get the same equation, not the same coefficient, but the same equation like this, divergence of some other conductivity gradient of the new U, the V in this case. And the F has not changed because the change of variables is the identity at the boundary. Okay, so this seems like bad news because there is not uniqueness. There are many conductivities that give rise to the same measurements in the anisotropic case. So this could be interpreted as a form of invisibility already, because if gamma is identity, the push forward of the identity will give rise to another conductivity that gives you exactly the same measurements. However, this change of variables does not respect, you want to have the Harry Potter undisturbed there, or you can put any conductivity that you like inside where Harry Potter is, and this cannot be done with this change of variables. So you have to do more to achieve invisibility. So now we come to the idea of transformation optics. It's very simple. Again, if the equation is invariant under transformation, meaning you get, when you make changes of variables that are the identity at the boundary of the clock, it's invariant, you get the same type of equation, not the same coefficients, then it's the same. So many physical equations in applications are invariant under changes of variables. So this leads to invisibility for many type of equations. So you want to make invisible the blue fish. So on the left in the virtual space you have a point P. And here the rays of light is a Cartesian system of coordinates. Right? It's like this. Okay, so what we want to do is have the rays of light, and in particular we want the waves, but let's do the rays of light first, go around like this so that they don't penetrate here. And we want to make the blue fish invisible. So the idea is to contract this ball. You take this ball here, you contract it to a point. That's the transformation. You send this to a point. Why do we do this? Because a point is invisible. You cannot see a point in any dimension. So the picture on the right, anything you put inside this blue ball here will be invisible because corresponds to a point by this transformation, and a point is invisible. That's it. That's the whole idea behind invisibility, and this transformation has to be the identity of the boundary. So it's very simple. And this is what the transformation is doing. So this is sending the point to the ball, and you see how the Cartesian system changes. So we did the opposite here. Here we went from here to the ball, but you can also blow up this point. Take this point and expand it to this ball. And this is what is described in these pictures here. The point, and it's very specific transformation. And this is the map that does this. And this is what we did in our paper. So it's a change of variables. It's called a diffeomorphism in the mathematics literature, which is the identity of the boundary. This map that blows up this point to the ball. And on the other way, you take the inverse map. And this is written precisely what it is. And this is the identity at the boundary that we wanted before. And in spherical coordinates in 3 dimensions, you take the identity in the ball of radius 2 here. So we know that we have the identity here, this vacuum. The currents go straight through. Then you take this map, and you take the push forward conductivity. Remember, that depends on the Jacobian transpose composed with gamma composed with the Jacobian. On the boundary of on the clock, the blue region that I mentioned before, that's the clock. And then in spherical coordinates, it can be written this way. So r equal to 1 is this ball is a radius, so radius 1, and this is a radius 2. For simplicity, the difference with Penry's paper, they took the ball R1 and R2. But 1 and 2 is the same thing. And you can see it's an isotropic. This is done when sign is not 0. R equal to 1 is the boundary of the clock. And you see that one eigenvalue is 0 of first order at the clock. And the theorem, and inside this, where Harry Potter is, or whatever you want to put here, whatever conductivity you like to put here, it will be, you can put anything you like, any arbitrary positive definite in the ball of radius 1 that you want to make invisible. And there is a theorem that says that the measurements that you get from this new conductivity, which is this on the outside here, on the clock, and it's arbitrary inside. It's the same as if were vacuum, is 1, the identity. Exactly the same. You cannot distinguish between this gamma tilde and gamma. And so you draw the papers, you draw the currents like I mentioned before. The currents go around. And when you measure outside here, it looks like the currents went straight through. And that's invisibility. That's all. There are two ideas. Use transformations, and then you use a specific transformation to transform the medium that you want to make invisible to a point. There are other things that are invisible. For instance, in dimension 3, a line is invisible. You cannot see it. And so you can play around, and I'm going to do that later with this type of things. It's a very flexible tool. This changing the index of refraction was used for acoustic waves in the Second World War to hide submarines from sonar, because the index of refraction, again, of the water depends on the temperature. So you are at the same level of the depth. You go to the colder regions, and the index of refraction will be smaller, so the rays of light try to avoid that region. Like I was mentioning before, you have a large gravitational field. But of course, some go through, but they take a long time to come back, and so on. Is to receive the echoes, you receive first these echoes for sonar. So this is the way it was done, an ad hoc way, because the index of refraction is related to temperature to hide these submarines. So this is what I want to do now. I want to do complete clocking, not just that the rays try to avoid the region, but some rays go through. And also we want to do it for the waves. Again, we take now Helmholtz equation. The only difference is the frequency here. So the equation is different. It's very similar, and the physical interpretation is different. So this is acoustic equation with density given by this familiar object now. The density before was the conductivity, is a square root determinant of G times G upper ij. And the bulk modulus is this. And then the G upper ij is like before, exactly the same in spherical coordinates. And the theorem is that this describes the acoustic waves with anisotropic density. Most materials in nature have isotropic, means this matrix is diagonal. But in order to have acoustic clocking, we want anisotropic medium. And the measurements is the same as this were the identity matrix. This is acoustic clocking, and this was noticed in the physics literature in these two papers. But it's the same as the other one is exactly the same principle. You do a transformation, this equation is invariant in the transformations as well, and it's a very simple consequence of the previous. And you can do this for Maxwell equations, which is light, propagation of light. So now we come back to what I said earlier. The epsilon and the mu are going to be, this is the electric permittivity, magnetic permeability is going to be anisotropic. It's going to be a matrix. It's a positive, definite, semi-positive, definite symmetric matrix. Remember, one eigenvalue was 0. So inside the clock where Harry Potter is arbitrary. This is called a Riemannian matrix, but just think of a matrix, an arbitrary positive definite matrix. And here is the one we found, is this one we found before, exactly the same as this. And the theorem is that the measurements are the same as in vacuum. In this case, the Dirichlet-Neumann map maps the tangential component of the electric field to the tangential component of the magnetic field. This is one first-order system before we have second-order equations. So you can also clock light with these materials, light and microwaves, radio waves, etc. And this is a blueprint. So I'm going to write it in terms of the radius of these balls here. The epsilon and the mu and the radial variables are given like this. In the phi, this angle here is given very specific, just depending on the radius, and in the theta direction. This is the 3 dimensions, which is the important one for invisibility, is given here. So we have a blueprint for invisibility. We know exactly what the epsilon and mu had to be here, therefore the index of refraction. Remember, the index of refraction is the square root of epsilon times mu. So that you have this effect, the light will go around, not only the rays, but the waves, because we're talking about solutions of Maxwell equations. And this was the case that started this, which is electrostatics. And this is a simulation of the waves now going around. And when you see them on the other side, it looks like they don't change. And you can do this from any direction, and you will have the same effect. So it's complete clocking. So you can do other things with transformation optics. I can make a transformation from real space to illusion space. So when people look at me, they will see something much better. And this is not just a joke, but these papers in physical review letters and in mathematics was Hongyu Liu, was my postdoc. I suggested to him to do this. An unfortunate thing in mathematics, that papers are always much slower. It takes more time to get them published. And this can be done for other type of waves, even at the very, very small, like atoms. For quantum clocking, Feynman had a visionary speech in 1959. And the no equations was here. It's an amazing predicted nanotechnology. There is plenty of room at the bottom, arguing that you could put all the information in the libraries of the world in the pin of a needle. And this is true. What I want to talk about is the problem of manipulating and controlling things in small scale. You can also manipulate quantum waves. So you have Schrödinger equation with a potential here, Now the parameters change with every equation. The physical interpretation is different. This is the effective mass, this is the potential, this is Planck constant. But however, the coefficients are exactly what we had before. It's the same, always the same. This is the universality of mathematics. I'm not going to have time to explain this. What this is, these parameters are singular at the boundary of the clock. You can find electromagnetic parameters or conductivities which are strictly positive definite, but you don't get exact clocking. You get approximate clocking to any desired approximation depending how close you are to the region of the clock. This can be done and proven that you can get approximate clocking that for all practical purposes is what you want. You can see only up to certain precision. You can only measure things with certain precision. So approximate clocking has been also subject of interest. I'm not going to have to jump over this to come to the applications. So we have the theory for clocking. We know exactly what the epsilon, mu, and the index of refraction had to be. But these materials cannot be found in nature because they will be invisible anyway. So the question is whether we can fabricate materials, artificial materials that have the epsilon and the mu that we want. For instance, negative index of refraction also has been another subject of interest for this. It has many applications, and clocking is another one. So this is an area of material science, metamaterials beyond materials that are fabricated artificially to get the desired one. Usually, it depends on the frequency of the waves, are built at the wavelength, so the inverse of the frequency. So for clocking, David Smith has his group at Duke did this for microwave frequencies. And see, these are C-shaped circuits, these circuits that are in layers here, and they have the epsilon and the mu that you want. Remember, the epsilon and the mu had to vary continuously approximately here. And we know theoretically what they have to do. And there was an experiment that was in YouTube, I couldn't find it recently, of a 12 centimeters long copper, which is very highly conducting, and 2 centimeters in radius, I believe. Very large. And then there was clocking in that case. You could not see it. For visible light, it's of course of big interest, and many laboratories are working on constructing the materials. And it has done for invisible light spectrum, but this is, you cannot see, this is of course very enlarged for very small objects that you cannot see with your naked eye anyway. The question of whether you can do this for visible light, which has higher frequency, but there is a range of spectrum in visible light, is open, and there will be if you can do this, will be very likely a Nobel Prize. You can also do the opposite in the laboratory. We cannot do experiments on black holes, obviously, but however, we can create electromagnetic black holes using the opposite idea of what I just did. So it's the inverse of what the matrix that we constructed. So light will be trapped here and cannot escape. For acoustic clocking, which is easier because the frequencies are lower, this has actually been done with materials, very simple materials, plastic and holes in very cleverly built so that the sound waves go around and don't penetrate. This is creating the perfect concert hall. So these are the experiments done by Chang in Berkeley. There are many Changs. So he's now president of Hong Kong University. For water waves, the equations for which is valid is for equations that are invariant and the transformations. That's all what you need. For water waves, then you construct this very similar to what Smith did for light in layers with pillars here in such a way that the water will go around and not penetrate here. Again, experiments have been done in the laboratory, nothing at the level of buildings or cities. But this is a nice idea. It's also for heat waves. You can do the same for heat waves, so to completely insulate a region from heat. For earthquake, this is an application that interests me because the country I come from has had many earthquakes, have given a lot of data to seismologists. The largest earthquake ever recorded was in Chile, was 9.5 in the Richter scale in 1960. Completely changed the geography of the south of Chile. And then experiments at the frequencies of seismic waves, not at the scale of a building or a city, were done by these authors. Let me finish by something that interests me also a lot, which is another analogy with general relativity. There is a possibility in general relativity of having wormholes. These have not been found yet. Gravitational waves were only found 9 years ago. So wormholes is a prediction, but they seem to be unstable. But this is a possibility of going to the future in the sense that there is a shortcut in space-time. So you can go through a wormhole rather than going around. And there is a very nice movie for the people interested called Contact that have a simulation of what is going through a wormhole. Yeah, a lot of things that are real now were science fiction at some point. And we have built electromagnetic wormholes for optics that have the same effect. So a device that functions like a wormhole for electromagnetic fields has been called Harry Potter's Invisibility sleeve. So here is the picture. Instead of blowing up a point like we did before, we blow up a line to form a cylinder. The outside of this cylinder will be done in the same way as before to make invisible. So these parts are invisible to electromagnetic waves. But you can see what's coming in, and you can, by putting inside what you like, the parameters that you like, electromagnetic parameters that you like, you can predict what will come out. So you're creating a secret connection. You only know what's inside between 2 points in space. So this is a simulation. This light goes around in this part of the cylinder. So the light comes in the middle, and then you can wiggle around, you can return, you can stay trapped, many things, whatever you want. This is a simulation. An end of the wormhole is a sphere, the other end is over an infinite chessboard and under the blue sky. And depending on the electromagnetic parameters that you put inside, you can see nice pictures here. For the people who know, this is like an hyperbolic metric, and in this case wiggles a lot. Any art effect that you would like to have. This is another picture. And these magnetic wormholes have been constructed in the laboratory by these authors. So this part it looks like it's a magnetic monopole, which of course we know that's not possible with Maxwell equations. There is a magnetic field, and suddenly appears another magnetic field, and you can create whatever magnetic field you like, but this is invisible to magnetic fields. So of course this is only an experimental so far. What to do with wormhole? This is science fiction. So there are many things. Since I'm running out of time, let me just finish. An amusing application is this one. You can have confocal lens, confocal glasses here. Half of the glass is in front and half is attached to wormholes. This part is invisible, but because of the properties of the wormhole, you can see everything in the back. You can wash your back, and that can be useful for some people. Okay, so there is a question of whether we'll see Harry Potter's cloak for the next Halloween. I don't know. Any sufficient advanced technology is indistinguishable from magic. Your cell phones will be magic 50 years ago. And you have to use your imagination. The important thing is that you can control electromagnetic waves, and that has to have applications because you can control the path, not only just for clocking, for other things. So what we have done is a transformation between Maxwell equations, which describes light, propagation of light. We have created an index of refraction such that light goes around. And Einstein's theory of relativity, you have a large mass, then it deflects light. So we have gone from Maxwell to Einstein and back. So thank you. Talking, yes.
Is the intuitively, I would guess, approximate cloaking, the material is easier built?
Yes, that's exactly right. That's why of the interest on that, because the other materials needs the parameters to be singular, vanish. So, but you don't need that. You want approximate clocking, which is enough for practical purposes. Well, that's a good question. That we don't know yet. Several people are working on this. What is the range of frequencies for which we will be able to do this? It cannot be done for all frequencies because that will violate causality because you need to go around in the same time, right? But for a band of frequencies, this is certainly possible. But the question is how large is the range? It's a very good problem. So the approximate clocking is done by just simply truncating what you have and defining to be arbitrary positive definite here. So as you approach the boundary of the clock, it approximates what you want. The observations for the parameter identity or one or whatever you want. Yeah. So nobody understood anything, or the opposite, which is not credible.
Can you do any other geometry?
Yes. Any geometry. This is very flexible. As I pointed out, my geometry and the geometry of this transformation optics here, the only thing that you need is transform your domain into a point. So you need a transformation sending the domain that you have to a point. Of course, in the case of a ball, this is very explicit. For more complicated domains, you may have to do, if it's not explicit, you may have to do numerical to find the map that sends one into the other, or approximate shape. Yes.
Is it detectable that something is cloaked? Like in this picture, for instance, you can see that the orange fish gets distorted a bit when you apply the mapping.
So it's already in.
Is it possible to detect that something has been cloaked in a region, for instance, like where the orange fish has been distorted because of the
Well, the way to beat this is by frequencies. So we discussed that you can do this at a range of frequencies. But you send a frequency higher than this, you're not going to. You can beat it. But the question, but you don't know which frequency to send. Fortunately, the higher the frequency, the harder it is, because X-rays are very high frequency rays. If you can cloak an X-ray, could mean a lot of trouble. Yes.
Is there any relation here to optimal transport or measured transport, and that you're mapping a domain?
You're mapping something, but I don't know whether this is. That would be an interesting thing, whether this is optimal in the sense of this transformation is. Yeah, that would be interesting to see.
There's like some.
Yeah, there is from the geometric point of view, there is a metric here which is the identity. Actually, you can have other metrics, not the identity. The vacuum is the most interesting one, but I'll map it to another one. And so the question is whether you are doing it. I don't know. Good question.
It seems like there's some I guess maybe superficial resemblance to like the Monge-Ampere.
The Monge-Ampere question, yes. Yeah, there is some connection. But I don't know whether this has been used in any. Yeah, so that will be interesting to look at.
Any other questions? If not, let's thank Gunther for the presentation.